My name is Nikita Melnikov. I am VP of Engineering at Atlantic Money. And today we'll talk about effortless concurrency, about financial systems, about its challenges, and how to use actor model to solve everything we need in this kind of systems. So about me, as I said before, I am VP of Engineering at Atlantic Money. Also, I am ex-Tinkoff Bank and ex-Tinkoff Investments. I have more than 10 years in fintech. I was working on high-load systems. We had more than 300,000 requests per second. And also, I love Scala, Golang, Postgres, and Kafka. Let's begin. Let's take a look on the agenda. We will cover a few topics. So we will go from the problem to the solution that I propose. So the problem is about financial transactions and what problems could we have. After that, we will shift to traditional approach and their limitations. And we, of course, speak about asynchronous processing, about Kafka, how to implement asynchronous processing using Kafka, why do we need it, how it could help us. And the main topic is actor model, of course. Let's start. So, what is financial transaction? We will use our company as an example, and we will review the standard process for our cases. Customer can create a transfer in our app. So, for example, you want to send $100 to 90 euros to someone. You're creating the transfer in our app. You send $100 payment to our app, and we can send euros to your recipient. Let's simplify it a bit. So we are waiting for dollars, we run some checks, we send euros. Sounds simple, right? But in fact, what happens in the real world? First of all, as we discussed before, customer creates USD to euro transfer. System waits for USD, the same as before, right? System writes the payment details. So we should know when we've got your payment, amount, sender, recipient, your bank information, and any other information that we need. After that, system runs some checks. What checks? For example, we must check sanction lists. We should check your payment in our anti-fraud system. We should check your payment limits. We should calculate fees and many more, as many as you can imagine. Of course, we have to exchange currencies to send another currency to your recipient. And finally, we can send euro to the recipient. Where is the problem? Of course, there can be many problems in terms of compliance, operations, finance, and so on. But we will review only one technical problem today. The problem is lost update. Let's take a look on the diagram. What happens here? So when transfer system receive your payment, we should find proper transfer in the database. After finding, we should check the sender and the recipient, for example, in our compliance service. We are getting, okay, everything is fine, so we can go further. We are processing the request, doing some calculations, applying fees, exchanging currencies, and finally we should update the transfers. So just to set the status that everything is fine, so we've paid out the money to your recipient. Where is the problem? The problem is when compliance system decided to cancel the transfer at the same time while we are processing the original transfer. So the process looks mostly the same, but after successful checks, the compliance service can decide to cancel the transfer. So it hits in point transfer/cancel, and we should select transfer for restriction and update transfer as well. Let's take a look on two transactions here. On the left, we have compliance transaction. On the right, we have our payment to our system. So we are starting the transaction, we are selecting transfer, we are getting result. So result is the same. So ID 1, status created, everything should be fine in both transactions. After that, we are setting different statuses. For compliance, we should set status cancelled. For our payment, we should set status payment received. Okay, cool. We're committing the changes. Where is the problem? The problem is here. If we will select transfer right after these changes, we can get undefined status. So because we have two concurrent transactions and we don't know what exactly we want to have at the end, and we cannot guarantee the order of these statuses. So the status can be undefined, it can be canceled, it can be payment received, or any other, of course. Let's try to solve it. And we will talk about traditional approaches. Of course, I don't have the time to provide all possible options how to solve it. And also we are limited by technology that we use now. Let's imagine we have Postgres database, right? And we can solve it like in that way. We have database transaction. How it looks like? The same as before, we are starting the transaction. We are selecting transfer for update now. And we can commit the changes. Everything is okay. Let's try to implement it on the diagram. So this is the same diagram as before, except just one small thing. Instead just of selecting the transfer, we are selecting it for update. We are starting from payment receiving process. So we are selecting for update, we are checking sender and recipient, everything is fine. At that moment, compliance system decided to cancel and restrict transfer. It does select for update as well, but it should wait until we have one open transaction for update for one single row or for many rows. Postgres knows that everything should be blocked until the first process will be completed. So the first process, when we are receiving the payment, is pending now. So we are selected transfer, we are doing some calculations, we are working on the processing, and finally we do update on the step 6. Once we committed changes, we can continue with the second process. We already sent select for update request from compliance service to our database, and we were waiting for the result, and now the result is finally here, and we can continue. Everything is solved actually. So everything is super simple here. So there are only 2 database transactions. We don't have any new abstractions or any new tools. But where is the limitation? Let's make a quick calculation. So let's imagine we have processing time, average processing time, 5 seconds. And we have 100 operations per second. That means that we should have 500 active transactions. Doesn't seem complicated, right? Postgres definitely could handle this. And yes and no. There are 2 drawbacks. First of all is resources. We have many active transactions that do nothing actually, because we are waiting, we are going to external services, we are writing some audit data, we are getting data from another service, so many things. So while we do this, transaction is active and we cannot work with this locked row, for example, with this transfer. And the second point is about your connection pools. So I believe most of you have connection pooling system in your apps. So for example, it can be limited up to 16 connections to your Postgres instance. And everything should be fine actually, because we have different transfers. But the problem will be if you have multiple concurrent transactions in the database. Let's imagine we have 16 concurrent processes at the same time. So that means that the first connection will be acquired by actual transaction. So we got the result from the database, we start doing something, we are processing, it took 5 seconds, and finally we can release. During this time, the second operation will be waiting, and the third and the fifth and the sixth and so on. The contention of on the lock and on the database, in fact, if we want to work with the same transfer, it will be quite a problem, because at the end you can end up with just empty connection pool, because every connection is busy and you cannot run anything else on these connection pools. You cannot serve customers' requests, you cannot serve another transfers. Here's the problem. Okay, let's try to solve it in another way. Let's try locks. Of course, locks can be implemented in different systems in different ways, but in fact today we'll talk about local locks and distributed locks. Let's start with local locks. In Golang, it can be done via just a mutex object. How it works? We should run something on the transfer. We are trying to acquire the mutex and defer a function to unlock it. If mutex was already locked, the coroutine will be pending actually. We will wait until the lock will be resolved. Everything is simple, right? But the problem is obvious actually. If you have multiple nodes, you have multiple endpoints or processes or whatever, or maybe your consistent router on Nginx or any another balancer was broken or after start, you can end up with this scheme. So one node holds a local lock for one transfer, and the node 2 got a request for the same transfer with different endpoint. That means that locks doesn't work at all, so you don't need it. Let's try another approach. So this is about distributed locks. Of course, it's become a bit complex, because you should introduce new infrastructure things here, and also you should understand how it works, and your engineers as well. So let's start with the diagram. So the key difference actually is that instead of just a mutex in a single node application, you have distributed lock manager. How it works? Node 1 can request for lock in a lock manager, and if it was not acquired by another process, we can run the lock. If node 2 will try to request the same lock, it will wait. So it works the same. So if node 1 has the access, it can safely access some resources. And if everything is done, so we can just release the lock, and right after that, lock manager will grant the lock to the second node. Everything is super simple here. About storages, actually there are a lot of options. We will just to name a few: Hazelcast, Zookeeper, etcd, Console, Redis, whatever you need, whatever you know, whatever you like, so you can use everything. What about limitations here? Limitations are quite complex actually, because under load it can be quite challenging to understand how the system will work because of problem of ordering. So let's imagine you have multiple nodes, for example a cluster with 16 nodes. They can be placed in a different zones, in a different data centers, in a different networks. Because of many things, it just have different timing to access your lock manager, for example Hazelcast, or for example Zookeeper. This is the first problem. So we cannot understand why we've got a lock to the node that, for example, call it later than the first one. So it is quite challenging to understand how it works, just because of problem of the ordering. Timeouts. There are actually multiple timeouts. So first of all, it is lock acquisition timeout. So we as engineers should understand, so I trying to get a lock in our lock manager. We should be able to set some timeout, because we cannot wait infinite time for this lock, because it will just hang in the process. And we should understand how to set this timeout, how to guarantee this timeout. And the second point is how to manage this timeout when we already acquired the lock. Let's imagine we've spent 3 seconds to wait for a lock, and now we should limit the time when we run actual logic, backend logic, right? And we already have 2 points here. So we should respect timeouts, we should respect holding timeouts, and we should understand how to work with them. What should we do if we didn't get the lock? Probably everything should be fine, right? So we just didn't do anything. What if we got the lock, but we lost the lock, or the process was crashed when we hold the lock? This is challenging, actually. So because you should respect it in your code. So every process should understand that it can be dropped, and the server can fail, and how to restore the process. And you should understand this partial state that was implemented during the lock holding. And of course, potential deadlocks. That means that, for example, we want to hold a lock for transfer, for check, for a customer, for a recipient, and to modify the state, we need to touch every object there. And potentially, it can be challenging to understand and to guarantee that there is no deadlock installed. Deadlock is when, for example, we've got a lock for transfer, we are trying to get lock for recipient, but other process started with the recipient and after the transfer. So the second transaction got a lock for recipient, and after that it's trying to get a lock for transfer, but it holding this lock is for the first node, for the first process, and it is quite challenging. I don't know how to guarantee that there is no deadlocks at all. Instead of just testing, but testing is super complex in distributed systems, so I don't have so many times to test distributed system on my own. Okay, let's try to switch to asynchronous processing. Let's first define what the transfer model is. Actually, it is finite state machine, right? Because of transfer has multiple statuses, state transitions occur via commands, each state defines load commands, and commands trigger actions and state changes. That's all. So finite state machine is same, right? So it's just switching before states because of something, because of some events or commands or whatever. So we cannot go from payment received to payment waiting just because it's impossible or in our domain. Let's take a look on the code. First of all, let's define transfer. For simplicity, it can have only ID and status. What is FSM here, finite state machine? So we have a transfer created, we have command receive payment, and we can move our transfer to payment received, right? So let's define statuses. We have created, payment received, check sent, checks pending, and so on. So all our tree of choices and transitions from status to status. And of course, we need to define a command. So a command is something that can happen in your application. It can be done via HTTP endpoints, gRPC endpoints, broker messages, time, or whatever. In fact, we need just something to tell to the transfer that it should move from one step to another. And let's take a look on the code. How could we handle this command? Of course, we won't review everything here. We will start with something super simple. So receive payment command. First of all, we should check the status. Code is simplified. We ignore error handling here, error cases, and so on. So just a pure logic. We should check the status. We've got a receive payment command. We know that status should be only status created. If not, we should throw some error. We need to write payment details, we have to set status, we have to save the state, and we should tell to the transfer that we need to run some checks to move the transfer further. Okay, cool. Requirements for asynchronous processing. So now we know the model. Now we understand the transfer is actual FSM model, and we need commands, we need messages, we need states. Let's make some requirements for our system. First of all, we need communication through messages. Messages are comments or events or whatever. This is something that we can tell from one service to another service that it needs to run something. Also, we need one-at-a-time message handling. That means that if we got a command for transfer A, only one command can be executed for this transfer. If we have the second, it should be queued somehow. Also, we need durable message store. That means that we should keep our messages for some time because of node failures, location failures, data centers failures, and many more, because of many reasons actually. So because if we would need to replay messages somehow, maybe we need analytics, maybe we deployed something broken and we need to restore the state on some date or time. And let's take a closer on communication through messages. Actually, here is super simple, right? So we have a producer, we have a consumer, we have something in the middle to deliver messages. Let's call it message broker. Producer send messages to broker, deliver messages to consumer. Consumer tells to the broker that everything is fine, so we can continue. And producer can send another message. The same. One at a time message handling. So we already discussed, right? So we want to send 3 messages, but at the same time, message consumer can handle only one. Our transfer queue is something that can order the messages by producing time, delivering message one by one to the consumer, and transfer queue should wait until we've got acknowledgement of that message was processed and everything is fine. And the same for message 2, for message 3. We can think about it as a log. So we have written something to the queue one by one, and it will be consumed by the consumer one by one as well, in the same order. About durable message store. So there can be a lot of examples actually, because we have many things that can break our system, right? So we need just something to replay the message if our message consumer was broken, or even if external service system is broken. That's all. Okay, let's talk about Kafka. And of course, Kafka is one of my favorite technologies overall. So yeah, let's begin with some basics because we need it just to understand how it works. Kafka have topic as a root entity in the architecture. So topic is just a feed. It can contain multiple partitions, 1 to unlimited, of course, like a reasonably unlimited. And Kafka is a distributed system by default, so it can be deployed in multiple servers, in multiple locations. So let's just think that we have 3 brokers, and they can coordinate the data somehow. So one topic has 3 partitions, and each partition will be placed on the broker. Of course, there are replication, some guarantees, some settings. but we don't need it for today. About partition offsets, as we told before, so we can think about this message queue as a lock. So one partition can have message 0, message 1, message 3. And partition is actually the sequence of the messages. So one topic can have multiple partitions. One partition can have multiple messages ordered by date time. About routing, the most interesting topic here. Let's think about producers and partitions. Let's imagine we have multiple producers and we have multiple partitions. So how can we know where to place a message? Because partitions can be written in concurrent mode. So we can write to partition 1 and partition 2 multiple messages at the same time. There is no problem. There are multiple options. First of all, of course, it is round robin. This is, we will write the partition 0, partition 1, partition 3, partition 0, partition 1, partition 3, and so on. The interesting thing here is what exactly we need is the key. Kafka will calculate hash of the key, and the message for the key will be placed into the partition. So for example, we have a transfer message. We have a key equals to transfer ID ABC. So if producer 1 and producer 2 will write the same message with the same key to the topic, so that means that both messages will be placed into one partition, into the same partition. So this is the thing that we should keep in mind, because this is how it will help us to solve overall concurrency things. And let's speak about producer guarantees. There are a lot of settings, so of course Kafka is a quite complex system in terms of how to set up it properly and correctly. But let's speak about the most simple things. We have an X setting, so that means that when producer write message to the topic, we can set this X settings. If it equals to 0, no acknowledgement is needed. So that means that Kafka leader instance will get the message and said, okay, I've got it, everything is okay. Of course, it has lowest latency because we don't write anything to the disk or in other servers. And of course, there is no delivery guarantees, because if you have a call to Kafka with X0, Kafka said that, okay, everything is fine, so I got the message, and right after that, the leader replica failed. That means that there is no message told because we didn't wait for that. X1 means that leader acknowledges the write. In case of leader failure, data loss is possible. So in this case, so the leader replica will tell to the producer that, okay, I got your message, I written everything to my store, but if the failure will occur, data loss is possible, as I said here on the slide. And X all in sync replicas, so that means that all followers of their leader should acknowledge the message. Of course, it has highest durability and highest latency. Okay, let's revisit our requirements for asynchronous processing again. Communication through messages, done. Durable message store, done. One-at-a-time message handling. This is interesting thing. Consumer requirements. We want to have one-at-a-time message processing. Each transfer should be processed by a single consumer. Consumer should be able to scale horizontally. And now we have an abstraction as consumer group. So we want to scale our application by servers horizontally. So it is super simple in Kafka actually. So we have a topic, we have multiple partitions, we have consumer group. So we can tell to Kafka that this instance, this consumer is related to consumer group A. And when we deploy two instances, the same consumer group will be respected in Kafka. So partition 1 will be distributed to consumer instance 1, partition 2 and 3 to consumer instance 2. Here's the limitation. So you cannot have consumer instances more than number of partitions in your topic. So just keep in mind, if you have, for example, 16 partitions in your topic, the maximum number of your application instances in the same group will be 16 as well. And we've got everything we need. Messaging system using Kafka. So here is everything that we decided to change, right? So we combined the system from abstractions that Kafka provides to us, their units. For producers, we have compliance commands, we have verifications commands, we have payments commands, we have many commands producers. We have partitions for our transfer topic, for transfer A, for transfer B, for transfer C, and we have consumers. So here is on the diagram, we have a routine of how we can handle and guarantee one-at-a-time processing, right? Because in the consumer group, we guarantee that the order of events within a single partition is ordered. Also, we have consumer groups, so we can handle multiple partitions at the same time, and there is no option to get a message for a transfer in multiple consumers at the same time, just because of routing. Because Kafka will route transfer A into partition 1, transfer B into partition 2, transfer C into partition 3, and that's all. Okay, what about the actor model actually here? Let's review its core concepts. First of all, actor is a fundamental unit. Asynchronous message passing, state isolation, sequential message processing, location transparency, fault tolerance, and scalability. It can be implemented in our asynchronous system, right? Most of this. But let's do important disclaimer. This is not full implementation of actor model as Erlang or Kafka or maybe another framework. We will use the actor model as a concept here, just to build the system. There is no need to implement all feature because we don't need supervision, location, transparency, etc. because we just don't need it because Kafka got all complexity into their domain. So we could think about actors as a processor of commands with some mailbox of messages for processing and state isolation in our actual state of the transfer or maybe user or recipient or whatever. We only need the fact that we can interact within messages. We have state isolation, we have sequential message processing, we call it one at a time message processing before. Well, we have fault tolerance because if our server will fail, consumer and restart after, it will join consumer group and Kafka will rebalance partitions over new set of consumers. And of course scalability, so we can deploy as many consumers as we want. Of course, it has a limitation up to the number of topic partitions. Okay, let's try to implement actor model in our system. Yeah, we will ignore some things of actor model here. It's just an inspiration and how it can be implemented in a tool that can help us to build it. Let's start with interfaces. So we need to have a storage. The storage is quite simple. So we have to create just to produce a new structure to work with that. So key here is for a key as for state. So new, get, and put, everything is simple. And as we discussed before, we have a Postgres. It can be sharded, maybe not, so it doesn't matter. So it can be Cassandra, it can be whatever you need, and even local caches, Redis, just MongoDB, whatever you need. We have an actor, so actor should have just one single function. It should be receive. Receive function gets state and command and should return new state. So it is just a function that knows about current state and the command and produces new state or of course error. Mailbox. This is actual mailbox for our Kafka. We have to know about key, state, and command, and that's all. So we will deploy our application. We will start consuming messages from transfer topic, and this actor mailbox will know about routing key, state, and command to call actor. And of course, command producer. Command producer is something just to tell to an actor about a new command or message. So of course it should know about key and command as well. So for example, through this interface, we can tell to compliance system or even self-transfer topic about, hey, you have a new command here. Oh yeah, and this is about what this types means here. Kafka consumer. Actually, everything is super simple here. So Kafka record has a key and has a value. Key and value just a pure array of bytes, and that's all. So we have to somehow to decode it into the type that we need. Also, we have a storage, so we will try to get the state from storage. If it's not found, we will try to create a new state here. After that, we pass state and command into actor, and we are getting new state. That's all. So everything we need is just to update the state. And here is the problem. Of course, we have a database and Kafka. So that means that we have a problem with double writes. Double write problem is when you have a Postgres and Kafka and you cannot guarantee the transaction here, because if Postgres will fail, overall transaction will fail. If Kafka will fail, we write state to Postgres, but we cannot send messages to Kafka. So let's adjust our code a bit. It calls outbox pattern. Actually, it's quite popular, so I believe many of you know about it. So we have a new transaction, and our storage should take transaction as an argument as well. Everything we need is to produce not only new state but effects as well. Effect is something that should be executed later. For example, sending to Kafka. In our case, we have new state and array of effects, and we need to persist everything all together in one single transaction. So there is no Kafka at all. If you need to send something to compliance actor or user actor, you can just put everything in your database. Here's everything is solved actually, but the last thing is how to deliver your messages from Postgres to Kafka. Actually, you have many choices. Since you have a Debezium, you have Debezium connector, so it can listen for wall lock and deliver messages to Kafka in your topic. Also, you can write your way how to manage this. It's just up to you. Another important thing is about toxic messages. As we discussed before, we will retry to consume the message if something goes wrong. For example, we've got a transfer command receive payment, but payment was already received, so that means that we should return some error and ignore the message. And of course, if you have a large code base or many developers, so it's possible that you potentially can miss something and process it incorrectly. Here can be toxic messages. Of course, you can build many things on top of it, but let's discuss it a bit later. Toxic messages are messages that cannot be perceived. Messages can be caused by incorrect message format, incorrect message version, incorrect message data, or logic errors. For example, incorrect actor state and incorrect message processing. What to do with that? So, for example, you can implement delayed messages. You can implement a counter in some system just to count how many times your external service failed. And right after that, you can mark your message as a toxic. So you cannot process it 10 times in 10 seconds. That means that it should be toxic, or division by 0, or incorrect status for your state, or anything else actually. So the fact that the toxic messages are messages that you should ignore, but you should handle it somehow. So this is just a simple dead letters queue. So that means that new state after receive method returned toxic error, and we want to handle this letter somehow later. So this is dead letters queue right in the Kafka as well, and we are producing the same record to dead letters queue. We can run some monitoring, analytics, anomaly detection, and many more. And let's review final implementation for Kafka consumer. As before, we have key and value, we have state and storage, we have new state, effects, and error. If error is toxic, so we can send it to dead letters for investigation or for alerting. And we have our box pattern here, and that's all. So actually, this is implementation for your Kafka consumer to work with a transfer or with your actor. Everything is done here. And let's just take a look on a small function here. So this is for how to handle commands in your transfer actor. As an example, we've got received payment command. For example, we already checked that the status is payment waiting or another status that we need. We are computing new state by applying payment details. We are creating new side effects. For example, send checks command to transfer, to move it further, and we can produce new transfer event for analytic purposes and return just a new state and effect. That's all. So this is the whole infrastructure logic for your actor. That's all. So you can reach it with your own logic, and everything, all complexity is not here, is in Kafka. So your code is quite simple here. Let's make a conclusion here. So by combining principles of actor model, And Kafka is a messaging backbone with its own patterns, of course, with additional deployment you need as Kafka servers and things that you need to set up Kafka correctly. Actually, for example, Amazon MSK does it pretty well, actually. And all concurrency issues can be handled by Kafka just because you're writing imperative code. You're doing things one by one. You don't need to think about, hey, here can be another process, so we need to lock it somehow. So we have just a queue of messages and asynchronous communication. So that means that we can just place a command for a transfer in ordered queue, in order topic, or in order partition in the topic, and your transfer consumer will handle it one by one. And that means that you just avoided concurrency at all. So there is no locks, there is no concurrent database transactions. You don't need to think about, I need to go for some data. Data can be inconsistent. If you need something, just place a command and another actor can tell the result back. So everything you need, just a finished state machine for your entity, or even maybe you don't need FSM at all. So you have simple counter, you have dead letters check. Actually, that doesn't need actors at all. So there's a lot of options how to manage concurrency, but this approach help us just to avoid it at all. Thank you, and questions?